Hi everyone, welcome to this presentation. In this video, I'll walk you through the way RNN processes the input data, which is sequential in nature, and how it utilizes the concept of time step to build the summarized or the memory of the entire network or RNN network. In this example, I'll be using random embeddings. I will pick up one sentence as an example, like I like the movie, and we will assign some random four-dimensional vectors to each of the tokens. So here there are four tokens, and to each of these tokens, we'll assign four-dimensional random vector. And this will be the input to the RNN at each of the time step. In the next few slides, we will see how the memory is actually built or computed by the RNN. So the input embeddings might look like this for each of the input token. So at time step 0, we look at the word I, and that will be pushed to the RNN cell at time step T0, the token number 1. And in this example, I'm taking the hidden state representation with just one dimension, and that's why you see one circle here. Input is associated with the weight and a bias pair. And since the input consists of four-dimensional vectors, so we need four weights as well in the weights matrix. So the input weights will be 0.1, 0.2, and so on and so forth. Essentially, the number of features in the weight matrix will be same as the number of features in the input. In this case, the bias is 0 because we are taking unidimensional or one-dimensional hidden state. So, and now the first step that the RNN does is does the dot product of the input embedding with the weight matrix. And it's simply the dot product or corresponding element, and you get a total value or summarized value. So it is like a weighted sum of the features. So the value is 0.09. The next step is going to be to accommodate the hidden value or hidden activations from the previous step. Now, in this case, there is no previous activation because we are starting to process the first token. So we can take arbitrarily the hidden state might have a value of 0. So the next step is to use the weight and a bias for the hidden state, and we just do the linear transformation here as well. So the output of this would be, so the total input we computed, and the memory which is basically 0 times this plus 0, and that gives you the value of the memory. And the net activation to the net input to the activation is going to be the sum of these two. So this will go to the tanh. So when you apply the tanh on this, you will get a value like 0.09 and can be considered as rounded off as zero point 0.1. So this is the output of the RNN cell at time step 0 when it processed the word. So that means the output here, the activation, which will go to the next time step, is 0.10. And this output is actually passed to the next step, next time step, and where it is going to be again accommodated in the next token. So for example, here the time step 1, we will follow exactly the same process. The token is like, and we have the embeddings for the word like, and we will do the linear transformation like we did in the previous step. And also we will do the weighting of the hidden activation from the previous step, which is 0.10. And that's the same step like before. And then we compute the net activation, and this will go to the next time step. So let's see the time step number 2, which is basically token number 3. The word is the, and again we will take the embedding for the word the, and it will also be going through the process of linear transformation like in the previous step. and we will process the hidden outcome from the previous step, and we apply the weights and a bias, and you get the net value for the activation function. And this can be the output of the activation function, and that goes to the next step. And let's see the next step. So time step number 3. And the last word in the sentence is movie. And for the token movie, we have the embedding, for example, this, and we will follow exactly the same process here also. We compute the linear transformation, and after that, weighting of the hidden activation from the previous step, and we add them together as a summarized view, and this is going to be the final outcome of the sentence, which is I like the movie. So the outcome of the sentence in terms of memory is going to be the value here, 0.175. I'll walk you through what is the intuition behind this meaning as well, so we have a better clarity then. So the final output of the sentence is 0.175, and this is summarized the representation of the whole sentence. So for example, this is a sentence, I like the movie, and this can be represented, or rather RNN thought I can represent the sentence like 0.175. And this value will be passed on to the subsequent layer. Let's say we want to attach a classifier. So we will attach a classifier. It can be a dense network followed by the softmax or a sigmoid layer for the prediction. So comparing the hidden state, so for each of the time step, we have the hidden state, let's say 0.1, 0.226, 0.056. What this actually means. If you see here time step 0, the word I, and that produces a kind of a neutral, summarized or other weight or hidden state value 0 0.1. Now the next word is like, which is a emotion word probably, and because of the embedding associated with like, RNN did the dot product, and you have a higher value. Look at the value 0 0.1 and now 0 0.2, which is significantly higher than the previous step. The next word is the, which is again kind of a neutral word, is doesn't carry any emotion. That is dictated by the, again, the embedding that we push to the RNN model. And you will see that from 0.22, it has come down to 0.053. That means the RNN is saying that I don't understand the word the in terms of sentiment or classification. The next word comes is the movie, and which has, again, a positive embedding, or rather the features in the embedding reflect a movie being something positive. And again, you will see the value of the hidden state from 0.053 is going up to 0.175. So the intuition behind the summarization of the dot product across the time step is to say that, yes, I understand this sentence, and this probably means positive or negative. This is why RNN is much better than the traditional neural network for sentence classification or sentiment analysis. So the final insight is the final hidden state captures the net understanding, and the RNN essentially updates the memory step by taking the current word and also the previous activation. And the activation path really followed these values that I walked you through, zero point 0.1 and finally 0.175. So the overall idea of RNN doing a sequential processing is to capture the essence of the tokens in a serial manner and produce the summarized representation for the sentence. And that can be fed to the downstream classifier, and it does a much better job than a traditional neural network. So embeddings play a significant role in recurrent neural network. Better the embeddings, or it is much easier for the RNN to produce a high quality summarized representation. So in the next video, I'll show you the Python implementation of the RNN classifier. See you in the next video.